Hi, welcome to our presentation. The topic we choose is NDN content poisoning mitigation, present by Aish, Jay, and Inu. In this presentation, the roadman is me. I'll introduce introduction and the related terms, and Aish will talk about network topology, and then Jay will talk about our simulation process. This semester, our project scope is to discuss and attempt to test some method that we recommended for content flushing in named data networking protocol, that is, NDN. In our presentation, we'll briefly cover the following point, but will not talk about details of them. A quick detour: what is the limit of the project scope? Briefly covers detection or prevention of current or further poisoned content data. Stopping or prevention of injection from the same malicious router that interested corrupted data. Preventing a cache pollution attack, where the size of the content store is attempted to be depleted. Trying to stop poisoned content data from being accessible by users or other routers. All of the points mentioned above are worthily to be tackled or their own merit. However, we commit ourselves to limit the scope of the project and choose not to focus on them. Although our focus is not on this point, we will still provide our thought and discuss these points to prevent or limit these issues. Our main goal is to mitigate content poisoning. We will discuss some methods for content flushings. This will occur in the content store of an NDN router, which houses named data packet. The mission is to flush this data packet, since we deem them to be malignant. Finally, we will route these cache flush packets to other routers to flush their content store. Get started with introduction of some related terms. Firstly, NDN, named data networking. It is a future internet architecture. It wants to move from the host to host, which is the traditional client-server module, to a content-centered distribution of data. The pros are its efficiency, low cost, and some additional mechanism implement for security. And second is cache flush. A cache flush removes data that has been or is expected to be accessed from storage. For our purpose, NDN node cache flush will occur in the content store, where it stores data packets to be sent to those who request it. In normal scenarios, large amount of data being cache flushed can massively improve performance. Third, content poisoning. It is a type of cyber attack. It is when an attacker injects fake and or modified information into a storage operators of the target. It accomplished this task through a malicious router, producer, or a compromised router. After a successful insertion of malicious data, it can spread in the NDN topology through its neighboring routers. Then let's turn to the importance of our project. The attack causes the router to become slower, as it causes delay in retrieving particular data. The legitimate data is sent to those who ask for those particular data packets. Consequently, it causes serious concerns for all parties involved, from the users to the producers. Finally, it makes the router slower as it takes up storage space and the corrupted data stays in the cache of the content store, causing it to become slower. In order to understand our project, the first thing we need to figure out is how content poisoning happens in NDN. A poisoning begins with a compromised router or bad providers and clients. They push forged poisonous data in popular content names, where it propagated to users globally. A router can theoretically mitigate content poisoning attacks. However, since a router has to do expensive computation, the packets are passed to users without verification, and when the data is added to the content store, it is then verified. But that still doesn't mean it will detect it correctly if something is erroneous. This means a goal for mitigation is to reduce this computation load on the routers. The reason we focus on this topic is because that NDN as a available substitution that already been more and more used for real life to substitute TCP/IP, as there's some leaks of TCP/IP was discovered. Risks led by the new structure should not be neglected. There were two methods that can totally avoid this problem. The first is to eliminate cache altogether, and the second is only transferring data from a static cache. However, both of these two methods are not helpful to the real-life cases. In addition, there is the aspect of false positive rate being high causing issues for all parties involved. Those are some past works that focus on the same topic. A method used for the mitigation of cache poison packets is a technique which is feedback-based, also called exclusion-based, where it allows a user to include an exclude field to avoid unwanted bad data. This works by leveraging the technique called content ranking, where a router ranks its cache copies based on three features that the user specifies to exclude. Number of exclusions in common phase. Therefore, cache copies with higher rank are more likely to be sent to user. This, however, relies on exclusion issued by clients and therefore can be compromised. Then, Aish will talk about the network topology.
Thanks, Feng. Let's first look at the goals of the project to set us up for the network topology examples. The first goal we wanted to accomplish for our project was to test our novel approach using a peer-to-peer mechanism with a limited number of hops to notify neighboring nodes of the occurrence of cache poisoning. Then, we also want to discuss the merits of limited number of hops when passing off cache flush packets to nodes. Then to discuss limited selection of where to pass packets using a smart selection method. In the final paper, we will give a clearer roadmap. However, the three methods we are strongly considering are: first, is known to have access to a larger number of nodes, then pass the cache flush packet to that node, or if a node hasn't been accessed in a while, and to facilitate communication, pass it to that node. Finally, if a node is known to have access to the same data packet, pass it to that node. Thus, at the end, we will have a discussion for comparing and contrasting with other methods of mitigating cache poisoning. Methods of cache poison mitigation. We will look at two of them, the basic and advanced. The basics for cache poison mitigation are caching only static files, since it requires no check after the initial insertion, and not to trust any user-supplied data, i.e. route the request but don't store the data. The advanced case, or the worst case, calls for dumping of all cache in the root, as it is deemed more beneficial to purge the content, even though only a subset of the content is affected. This is done by going through the root of the directory and purge all the information stored in the content store pertaining to it, and wait for the user interest packets to restock the content again. This also has the positive consequence of a speed boost for the router. For NDN, there are two ways to run a simulation. One is NDN sim, the other being mini NDN. Let's take a look at the pros and cons. In terms of the programming language supported, NDN sim uses C++, mini NDN uses Python. For the members of our group, Python is a more comfortable language, while C++ required a certain learning cost. In terms of available platforms, NDN sim supports macOS, Windows, and Linux, but mini NDN only supports Linux. Finally, we chose mini NDN as our simulator, for it has an extensive and helpful documentation compared to mini NDN. Let's take a look at the recommended solution evolution. The first was brute force. In brute force, we would send a cache poisoning packet to every known node from patient 0. This guarantees if a node is connected to the topology, it will know that it has to delete that data packet. However, this will cause a flash flood since each router distributes the packet at least once, and it could also cause persistent flooding. The next step in the evolution is limited distribution with smart selection, which we talked about earlier. Similar to brute force, where each node sends the request, but in this case only to a subset of nodes it knows, as smart selection works. This will only pick nodes which it knows are connected to very few nodes in the topology and those that have that data packet. And the next step in the evolution is the same as the previous method, however now we include a limited number of hops. This will ensure a greater certainty that each node that is affected gets the cache flush packet, and it will also exponentially limit flooding and time wasted on the process. Finally, the last step would be the server can take over the process, since they would be notified of a malicious actor. If any router is still unnotified, they can be helped. We will explain our algorithm using this network topology example. In each of the next 3 scenarios, the node structure of having the knowledge of its neighbors will be the same. And in all scenarios, the same router will begin propagating cache flush packets, which will be known henceforth as patient 0. The first example being the brute force case, patient 0 begins the process by sending the packet to 3 nodes that it knows. This will cause flooding to persist in the topology, since every node will broadcast at least once when it receives that specific cache flush packet, as we can see with the patient 0 receiving its packet back. The next case is limited selection with smart selection. Patient 0 node propagates to all nodes it knows. However, henceforth, the nodes will use smart selection to properly push the packets. As we can see in the middle, the node has a data packet that it needs to flush. However, it isn't contacted. Thus, in this scenario, it is unaffected. Finally, in addition to the previous example, now we add a limited number of hops. The limited number of hops has the benefit of reaching nodes that it would have previously missed, since each node only contacts other node once. But in the limited number of hops case, it will keep contacting until there is a hop left. And as we can see in the middle, we finally reach the node that needs to get rid of the data packet. Alright, let's take a look at the downside of each approach. For brute force, we know the packet will be reached. However, the network will be under considerable flooding. The method limited selection with smart selection will be better in terms of preventing flooding. However, each packet will not reach every node. Finally, limited selection with hops. It's an improvement over the second method since we can implement a hop counter, and this will help us reach nodes that were initially missed and will prevent severe system flooding. But there needs to be further research done to see what the hop counter should be, since if it is very low, not every node can be reached, but if it's very high, then we run into the same problem as brute force with flooding. Now let's talk about some additional scenarios that we will expand on in the final paper. First being false positive. In order to decrease false positive rate, what we recommend can be done is to improve the test method or do multiple rounds of detection. But that multiple detection will certainly lower the efficiency. And the next scenario that we would want to discuss in further detail is whether to flush the packet or flush the hierarchy of the packet. We would want to balance whether the source is contaminated or just that packet was contaminated. And we would also have to consider that if the hierarchy is not purged, it can cause lots of harmful effects. Now I'll pass everyone off to Jay.
Thank you, Ayush. The first step in simulating using NDN Sim is setting up the environment. We start by attempting to build it on macOS. but we noticed that we were getting compilation errors pretty consistently at around 1800 to 2000 out of 2700 processes. So we reviewed some suggestions posted on the internet by others who'd also had similar issues to us. Someone suggested using NS 3.25 instead of the latest version because the errors may be caused by mismatches in the version numbers of GCC and NS3. But the previous version of NS3 had already been deprecated, so we couldn't install it. It was no longer available on GitHub either. We did actually manage to find a defunct version of NS 3.25 in a Mercurial repository later on, but that's for later. So we tried to install Xcores first, another suggestion from the internet, then set up the environment, but it still wasn't working. At this point, we could successfully set up with Python disabled on macOS, but since Python was disabled, we couldn't use the visualizer, which would make analysis harder. So we were wondering if we could run NDN sim with Python on Linux so that we could utilize the visualizer. Our first attempt was to try it on the lab machines, but we found out pretty quickly that you couldn't use sudo commands on those. So at this point, we were able to run the example scenarios that come with NDN and create some basic scenarios of our own using the components that already come with NDN. Unfortunately, for the kind of scenarios that we want to run, we had to implement novel classes such as poisoners and poison packets, as well as functions such as cache flush. So we attempted to create these new classes, followed the official documentation and the examples that we found online, but immediately stuff started failing again. I could honestly go on for a while talking about all of the different solutions, environments, and fixes that we attempted over the past few weeks. But honestly, NDN sim just didn't want to seem to run on any environment that we had access to. We tried Mac, Linux, Ubuntu using WSL2 on a Windows machine. We used Docker containers, which is the closest we came to actually simulating using our own code. But we were unable to execute after compilation. We scoured Google for solutions for each of these individual issues we faced. Someone said that our version of NS3 and NDN sim may be incompatible. So we tried downloading different versions from each, the respective GitHub repos of each. We also tried using an older deprecated version of NDN sim from Mercurial, and we had to switch to using Python 2 to be able to work with it. But inevitably, every new environment we tried to work with would come up with an entirely new issue that we just did not have a solution for. Ideally, we could have shown a visualized demo of a simulation, but not a single environment that we tried setting up NDN sim in would let us configure it with Python enabled for visualizations. So instead, we'd hope to have an output similar to this, giving an idea of the performance of our simulations. Unfortunately, for all the reasons we've listed already, and honestly many, many more, this just wasn't possible for us. Honestly, the whole experience has been pretty disheartening and disappointing because NDN is generally really interesting and promising technology, and it would have been really exciting to be able to make a contribution, even a minor one, to such an important project. Our final recommendations are as follows, though they do come with the giant asterisks of not coming backed up with the quantitative data that we would have liked to use. So firstly, an algorithm called smart selection, which pushes cache flush packets to the affected nodes with high certainty. Secondly, having a flag for designating a router as malicious and letting other routers and producers know. And finally, the cache flush packet. So for the cache flush packet, it should contain the packet name to purge and the number of hops to complete if initialized in a field. It should begin by a patient 0 router and be sent to nodes it knows using brute force or limited selection with smart selection. In the NDN router, the system should maintain a record of this flushed packet to notify any affected producers. And if the node that receives the cache flush packet does not have that packet, perhaps it can be allowed to drop the request, since with conjunction with smart selection, the packet name is not widely used. So, in conclusion, while we're all obviously very disappointed about not being able to back our data up with the simulations that we'd intended to, we nonetheless do still stick with our recommendations of using limited selection and cache flush packets. And also, we just look forward to discussing this more in depth with you guys. Please hit us up with like all the questions that you possibly can. Thank you.